Okay, in this chapter we're pretty much doing what we did in 3B, and we're doing a regression analysis. So when we have our bivariate data and we go through all the processes of doing the scatter plot, getting the equation and commenting on the scatter plot and the regression line and things like that. So we're going to do another one, and we're going to use this example, birth rate and life expectancy. So they measured the birth rate in 10 countries and also their life expectancy. So here they're thinking that if the birth rates increase, the life expectancy may change. So here it's important to work out at the start which is your explanatory variable and which is your response, because it will make a difference with everything. So in this example, birth rate is going to be our explanatory variable, and life expectancy is what we're looking at, and we want to see what happens if we change the birth rates in the country. Does the life expectancy change? So that's our response variable. Okay, so moving on, we put in the data into our calculators, and I've created a scatter plot. So I've just put the screen dump of the calculator there. So you can see we've put the EV along the birth rate on the x-axis and life expectancy on the y, which is the response. So the first thing that we're going to look at is the correlation coefficient. So I've gone back to where I put my lists in list and spreadsheets, and that's where I'm going to find all the R value and plus the A and the B value. So remember, we go to menu and we go to stat calc and the linear reg. So I can see here that my R value is listed here, and it should be negative because the graph is a negative graph. So I'm going to write down my R value. I'm going to say to 4 decimal places because that's pretty common for an R value. So negative 0.0869. Okay, so we've got 4 decimal places there. And now it's asking, the next thing we need to do is get the least squares regression line. So that's when we must use the variable names. The least squares regression line is actually y equals a plus bx, but we don't want to use y and x anymore. We want to use our variable names. So I'll say life expectancy, and I might put the units in brackets, which was years, equals. Now I'm going to do the a value here, the first off, and here's our a values. And I'm going to go to 3 significant figures. So if I do 3 significant figures for the A value, it'll become 105. And then we're going to do minus the B value because it's a negative, because this graph is going down. It's a negative B value, negative gradient. So 3 significant figures would be negative 1.44. And then we're going to times it by the explanatory variable, which is birth rate. And we might put the units in the brackets, which was per thousand. Okay, and there we go. So the next question asks us to interpret the slope. So if you go to your notes, you'll see we have the templates to interpret the slope. So I've gone to the negative one, obviously because it's a negative B value. Now we don't need to put, we don't need to put that it's a negative, that obviously that's the one you're picking, but you then write out the next statement. So the slope estimates that on average the life expectancy to decrease by the B value, so 1.44. Now we don't need to put the negative there because the word decreases indicates negative. So decreases by negative 0.44 when the birth rate increases by 1 per, and you might just put in brackets the per thousand, the units for EV. Okay. Then we're asked to interpret the vertical axes. So that is there when we talk about the vertical axis here. That's another way of saying the vertical axis intercept is the y-intercept, or we know it as it's the a value that they're talking about. Okay, so if we go to interpret that, once again, we've got a little template. We're going to write this out. So the regression line intercept predicts the average value of the life expectancy to be, and we're going to put the a value. So we just delete, oops, sorry. We don't want to delete all the words. You should be writing this out, but we're just going to pop in here, the life expectancy to be, and what are we going to say? The a value. So 105 years when the birth rate, and we just put in brackets per 1,000, is 0. Okay, moving on, we're going to be asked to predict. So we're going to be using the equation that we found. So the equation we found is the life expectancy to equal 105 minus 1.44 times birth rate. Okay, so we're going to use that and we're going to make some predictions. And here they're going to ask us, ask us what is the life expectancy when we have a birth rate of 35 per 1,000. So we just pop that into the formula, and where we see the EV, or the birth rate, we're going to put 35. So we're putting that in there, and we'll get an answer. And we get 54.6 years. Okay, then they ask us to predict the life expectancy of a country with 20. So we do the same here, but except we're going to put in the 20, and we get an answer of 76.2. Okay, the next thing they do is they ask us if it's comment on the right reliability of these predictions. So over here, I put the scatter plot to show you. In the yellow here, if we predict within the range, and so that means the lowest X value, which looks like 26, and up to, say, 43 or whatever for the highest X value there, this one and this one. If we predict within those numbers, it's interpolating, and we can say it's a reasonably reliable result because we can see data around those points. If you predict outside, so that would be anything before 26 or anything after that 43, that's called extrapolating, and we can see it's not as reliable. So you would just write a little comment that when we predicted the 35, that was interpolating, so therefore it is reliable. And then when we predicted the 20, that was outside, so it's extrapolating, so it's not as reliable. So the next one asks us to interpret the coefficient of determination. Once again, you have a little template that you have to use, and if we went back to look at our stats, we can see the R squared was actually, so if I write down what the R squared was, it was actually 0.6510. So when they ask us to interpret it, we say the coefficient of determination tells us, now we change that to a percentage, so we times it by 100. So I might say 65.1% of the variation in, now here is where I'm going to delete this response variable, and you're going to write what it actually is. So in this example, so the variation in life expectancy is explained by the variation in birth rate. Okay, and there we have that. We're interpreting that. Then we've asked to produce a residual plot. So we went through that the other day. So once we've got the scatter plot, remember you need to pop this regression line on the scatter plot, and then you should be able to analyze and produce a residual plot. So I can see here, this bottom graph is the residual plot, and this top one is the original scatter plot. So we can look at that, and when we look at the residual plot, we need to write a little comment, and plus it's in your notes already. So I can say this original scatter plot, the original one is linear, as from the residual plot, we can see there's no clear pattern. So in this one, we're seeing no clear pattern, and no clear pattern in the residuals. This confirms our original assumption that a linear relationship is occurring. So we would just say, as there's no clear pattern in the residual plot, we can confirm our assumption that the data is linear. Okay, so here I've gone through, I've got a couple of regression analysis questions that you could get on your exam. And obviously this was from the 2016. It's all question 3, and in total it's going to make up 8 marks. So if we go through it. So the data in the table below shows a sample of actual temperatures and apparent temperatures recorded at a weather station. The scatter plot of the data is shown, and the data used to investigate this association is between the variables apparent temperature and actual temperature. So here we might not know, if we looked at the table, which one actually is RV and EV, but because they gave me a scatter plot, I can see that apparent temperature is on the y-axis, so apparent temperature is apparent temperature is RV. So that means I know that this one's EV. So this is the Y one and this is the X one. Okay, so use the scatter plot to describe the association between apparent temperature and actual temperature in forms of strength. So strength is where you say it's strong or weak. So you don't even have to type in the data. We've been given the R squared value there. So the R value would be the square root of that number. So if I did the square root of that R squared number, I would get don't need to write that. I'm going to get an answer of 0.98, and we're going to leave it as a positive because this is a positive graph. So now we know the strength is definitely strong. So we're going to say a strong is the strength, and then it says direction. So it's going up in a positive direction. So strong, positive, and we're going to say it looks like a linear exam. Okay, so use this to describe the association. So we can just say it's strong, positive, linear. Okay, there's our 1 mark. Sorry. Okay, next it's asking us to determine the equation of the least squares regression line, and it's asking us to 2 significant figures. So you've put the data in to the calculator, and you're going to find the A value and the B value to 2 significant figures. Okay, so I've just popped in those 2 lists into the calculator, and I'm just showing you what happened. So when so remember that the actual was your EV and the apparent was your RV. And so I get these, I can see the A and B values, and a good way to check, I got the R squared, which was the same as what they said on the other page, so that's good. So now they're saying 2 significant figures. So for the A value, it's actually a negative and 1, and then 6 would be my second, but because it's a 5, I have to go up. So there's 2 significant figures for that one. And for B, it would be 0.9 and 4, because the next one's 2. So, and then it says interpret the intercept of the least squares line in terms of the variable apparent and actual temperature. So we just go grab that template again. Okay, so I found the interpret the intercept thing here again. So the regression line intercept predicts that the average value of apparent temperature to be, and then you put the A value, so negative 1.7 when the actual temperature is 0. Okay, and the coefficient of determination for association between the 2 variables is 0.97, and interpret the coefficient of determination. So that's when we get the the blurb for the R squared value. Okay, so the coefficient of determination tells us that 97% of the variation in apparent temperature is explained by the variation in actual temperature. So I would write all that out following that template again. Okay, and it said a residual plot can be used to test the assumption of the nature of the association between these two numerical variables. What is the assumption? So we assumed it was linear. Okay, and does the residual plot support this assumption? Explain your answer. And I'm also going to say yes, it does support the assumption, as there is no clear pattern in the residual plot. Okay, so we've got a couple of exam multi-choice questions here. So really important we start making sure we read everything. So read the blurb at the start. The scatter plot shows life expectancy plotted against human HDI in a large number of countries in 2011. The least squares line has been fitted and the resulting residual plot has been shown. So they've even given you the least squares equation. They've given you R squared there. Given the information, which statement is not true. So they've asked for the value of in the first one, the value of the correlation coefficient is 0.94. So we want to check for the R value. So remember the R value is the square root of the R squared, which they gave me there. So I'm going to do that. Okay, so when we do square root of that, we get 0.94. It does round to that, and it's positive because this graph's positive. All right, so which one they want is not true. So we just found that to be true, so that's not good. Now it says 12.5% of the variation is not explained. So that is the blurb for the R squared value. So if you look here at our R squared value, if we change that to a percentage, it would be 87.5%. So we'd say 87.5% is explained. So what is not explained is the rest. So 12.5% would add it up to 100 is not explained. So that statement there is also true. So on average, life expectancy increases by 43 years for each 10-point increase. So when they say on average an increase, they're talking about the B value, which was here. Now the B value is not the 43, that's the A value. And if you times this HDI by 10, it would only increase it by 4.2. So this one is not correct. So I'm going to go with C being the answer. Ignoring any outliers, the association between life expectancy and human development is a strong positive linear. That looks like a true statement as well. And using the least squares line to predict life expectancy in a country development index of 75 is interpolation. Well, that is true because we've got between 25 and 95. That's in interpolation up there. So that is true. So we're definitely happy with the C. Now in question 10, it says in 2011, the life expectancy in Australia was 81.8 years with a human index was 92.9. So that's the X value, the X value there given, and this was a Y value given. So this was an actual data point. And then they say when the least squares is fitted, the residual. So if you write out the formula for residual is actual minus the predicted. Now, I've always said that the actual is the dot, or they might give it to you in the table of values, or they actually gave it to me, and it was 81.8. And then you've got to minus your predicted. So your predicted is when you use the equation. So up there, you'd be 43.0 plus 0.422 times the HDI, which they told us was 92.9 in this case. And you get negative 0.4038. So I'm going to go B, negative 0.4.